can you describe this fascinating field of mechanistic interpretability, aka mech interp, the history of the field and where it stands today?
I think one useful way to think about neural networks is that we don't program them, we don't make them. We grow them. We have these neural network architectures that we design, and we have these loss objectives that we create. And the neural network architecture, it's kind of like a scaffold that the circuits grow on. And they sort of, it starts off with some kind of random things, and it grows, and it's almost like the objective that we train for is this light. And so we create the scaffold that it grows on, and we create the light that it grows towards. But the thing that we actually create, it's this almost biological, entity or organism that we're studying. And so it's very, very different from any kind of regular software engineering. Because at the end of the day, we end up with this artifact that can do all of these amazing things. It can, write essays and translate and, understand images. It can do all these things that we have no idea how to directly create a computer program to do. And it can do that because we grew it. We didn't write it. We didn't create it. And so then that leaves open this question at the end, which is, what the hell is going on inside these systems?
Mm-hmm.
And that, is, to me, a really deep and exciting question. It's, a really exciting scientific question to me. It's sort of is like the question that is just screaming out. It's calling out for us to go and answer it when we talk about neural networks. And I think it's also a very deep question for safety reasons.
So, and mechanistic interpretability, I guess, is closer to maybe neurobiology.
Yeah, I think that's right. So maybe to give an example of the kind of thing that has been done that I wouldn't consider to be mechanistic interpretability, there was, for a long time, a lot of work on saliency maps, where you would take an image and you try to say, the model thinks this image is a dog. What part of the image made it think that it's a dog? And, that tells you maybe something about the model, if you can come up with a principled version of that. But it doesn't really tell you, like, what algorithms are running in the model. How was the model actually making that decision? Maybe it's telling you something about what was important to it, if you can make that method work. But it isn't telling you, what are the algorithms that are running? How is it that the system is able to do this thing that no one knew how to do? And so I guess we started using the term mechanistic interpretability to try to sort of draw that divide, or to distinguish ourselves in the work that we were doing in some ways from some of these other things. And I think since then it's become this sort of umbrella term for, a pretty wide variety of work. But I'd say that the things that are kind of distinctive are, I think, this focus on, we really want to get at, the mechanisms. We want to get at the algorithms. If you think of neural networks as being like a computer program, then the weights are kind of like a binary computer program, and we'd like to reverse engineer those weights and figure out what algorithms are running. So, okay, I think one way you might think of trying to understand a neural network is that it's kind of like we have this compiled computer program, and the weights of the neural network are the binary. And when the neural network runs, that's the activations. And our goal is ultimately to go and understand these weights. And so, the project of mechanistic interpretability is to somehow figure out, how do these weights correspond to algorithms? And in order to do that, you also have to understand the activations, because it's sort of, the activations are like the memory. And if you imagine reverse engineering a computer program, and you have the binary instructions, in order to understand what a particular instruction means, you need to know what is stored in the memory that it's operating on. And so those two things are very intertwined. So mechanistic interpretability tends to be interested in both of those things. Now, there's a lot of work that's interested in those things. Especially there's all this work on probing, which you might see as part of being mechanistic interpretability, although it's, again, it's just a broad term, and not everyone who does that work would identify as doing mech interp. I think a thing that is maybe a little bit distinctive to the vibe of mech interp is, I think people working in this space tend to think of neural networks as, well, maybe one way to say it is that gradient descent is smarter than you. That, gradient descent is actually really great. The whole reason that we're understanding these models is because we didn't know how to write them in the first place. That gradient descent comes up with better solutions than us. And so I think that maybe another thing about mech interp is sort of having almost a kind of humility, that we won't guess a priori what's going on inside the model. And so we have to have this sort of bottom-up approach, where we don't really assume, we don't assume that we should look for a particular thing and that will be there and that's how it works. But instead, we look from the bottom up and discover what happens to exist in these models and study them that way.
But, the very fact that it's possible to do, and as you and others have shown over time, things like universality, that the wisdom of the gradient descent creates features and circuits, creates things universally across different kinds of networks that are useful. And that
Yeah.
makes the whole field possible.
Yeah, so this is indeed a really remarkable and exciting thing where it does seem like, at least to some extent, you know, the same the same elements, the same features and circuits form again and again. You can look at every vision model and you'll find curve detectors and you'll find high-low frequency detectors. And in fact, there's some reason to think that the same things form across biological neural networks and artificial neural networks. So a famous example is vision models in the early layers. They have Gabor filters, and there's Gabor filters are something that neuroscientists are interested in and have thought a lot about. We find curve detectors in these models. Curve detectors are also found in monkeys. We discover these high-low frequency detectors, and then some follow-up work went and discovered them in rats or mice. So they were found first in artificial neural networks and then found in biological neural networks. There's this really famous result on like grandmother neurons, or the Haley-Berry neuron from Quiroga et al. And we found very similar things in vision models where, this is while I was still at OpenAI, and I was looking at their CLIP model, and you find these neurons that respond to the same entities in images, and also, to give a concrete example, we found that there was a Donald Trump neuron. For some reason, I guess everyone likes to talk about Donald Trump, and Donald Trump was very prominent, was a very hot topic at that time. So every neural network that we looked at, we would find a dedicated neuron for Donald Trump. And that was the only person who had always had a dedicated neuron. Sometimes you'd have an Obama neuron, sometimes you'd have a Clinton neuron, but Trump always had a dedicated neuron.
Yeah.
So it responds to, pictures of his face and the word Trump, like all of these things, right? And so it's not responding to a particular example, or like it's not just responding to his face. It's abstracting over this general concept, right? So in any case, that's very similar to these Quiroga et al. Results. So there's evidence that this phenomenon of universality, the same things form across both artificial and natural neural networks. So that's a pretty amazing thing if that's true. It suggests that. Well, I think the thing that it suggests is that gradient descent is sort of finding, the right ways to cut things apart in some sense that many systems converge on, and many different neural networks architectures converge on. That there's some natural set of, there's some set of abstractions that are a very natural way to cut apart the problem, and that a lot of systems are going to converge on. That would be my kind of, I don't know anything about neuroscience. This is just my kind of wild speculation from what we've seen.
Yeah, that would be beautiful if it's sort of agnostic to the medium of the model that's used to form the representation.
Yeah, and it's a kind of a wild speculation based. We only have a few data points that suggest this, but it does seem like there's some sense in which the same things form again and again, certainly in natural neural networks and also artificially, or in biology.
And the intuition behind that would be that in order to be useful in understanding the real world, you need all the same kind of stuff.
Yeah, well, if we pick, I don't know, like the idea of a dog, right? Like, there's some sense in which the idea of a dog is like a natural category in the universe or something like this, right? Like, there's some reason, it's not just like a weird quirk of like how humans think about the world, that we have this concept of a dog. It's in some sense or like if you have the idea of a line, like there's, like look around us, there are lines, it's sort of the simplest way to understand this room in some sense is to have the idea of a line. And so I think that would be my instinct for why this happens.
Yeah, you need a curved line, to understand a circle, and you need all those shapes to understand bigger things. And
yeah,
it's a hierarchy of concepts that are formed. Yeah.
And like maybe there are ways to go and describe, images without reference to those things, right? But they're not the simplest way or the most economical way or something like this. And so systems converge to these strategies would be my wild hypothesis.
Can you talk through some of the building blocks that we've been referencing of features and circuits? So I think you first described them in 2020 paper, Zoom In, an introduction to circuits.
Absolutely. So maybe I'll start by just describing some phenomena, and then we can sort of build to the idea of features and circuits.
Wonderful.
So if you spent like quite a few years, maybe like 5 years to some extent, with other things, studying this one particular model, Inception V1, which is this one vision model. It was state of the art in 2015, and very much not state of the art anymore. And it has, maybe about 10,000 neurons in it. And I spent a lot of time looking at the 10,000 neurons of Inception V1. And one of the interesting things is, there are lots of neurons that don't have some obvious interpretable meaning, but there's a lot of neurons in Inception V1 that do have really clean interpretable meanings. So you find neurons that just really do seem to detect curves, and you find neurons that really do seem to detect cars and car wheels and car windows and, floppy ears of dogs and dogs with long snouts facing to the right and dogs with long snouts facing to the left and, different kinds of fur. And there's sort of this whole beautiful edge detectors, line detectors, color contrast detectors, these beautiful things we call high-low frequency detectors. I think looking at it, I sort of felt like a biologist. You're looking at this sort of new world of proteins, and you're discovering all these different proteins that interact. So one way you could try to understand these models is in terms of neurons. You could try to be like, there's a dog detecting neuron and here's a car detecting neuron. And it turns out you can actually ask how those connect together. So you can go and say, I have this car detecting neuron. How is it built? And it turns out in the previous layer, it's connected really strongly to a window detector and a wheel detector and a sort of car body detector. And it looks for the window above the car and the wheels below and the car chrome sort of in the middle, sort of everywhere, but especially on the lower part. And that's sort of a recipe for a car, right? Like that is, earlier we said the thing we wanted from Mech was to get algorithms, to go and get, ask what is the algorithm that runs? Well, here we're just looking at the weights of the neural network and reading off this kind of recipe for detecting cars. It's a very simple, crude recipe, but it's there. And so we call that a circuit, this connection. Well, okay, so the problem is that not all of the neurons are interpretable. And there's reason to think, we can get into this more later, that there's this superposition hypothesis. There's reason to think that sometimes the right unit to analyze things in terms of is combinations of neurons. So sometimes it's not that there's a single neuron that represents, say, a car, but it actually turns out after you detect the car, the model sort of hides a little bit of the car in the following layer and a bunch of dog detectors. Why is it doing that? Well, maybe it just doesn't want to do that much work on cars at that point, and it's sort of storing it away to go and so it turns out then that this sort of subtle pattern of, there's all these neurons that you think are dog detectors, and maybe they're primarily that, but they all a little bit contribute to representing a car. In that next layer. Okay, so now we can't really think there might still be something that I don't know, you could call it like a car concept or something, but it no longer corresponds to a neuron. So we need some term for these kind of neuron-like entities, these things that we sort of would have liked the neurons to be, these idealized neurons, the things that are the nice neurons, but also maybe there's more of them somehow hidden, and we call those features.
And then what are circuits?
So circuits are these connections of features, right? So when we have the car detector, and it's connected to a window detector and a wheel detector, and it looks for the wheels below and the windows on top, that's a circuit. So circuits are just collections of features connected by weights, and they implement algorithms. So they tell us, how are features used? How are they built? How do they connect together? So maybe it's worth trying to pin down like what really is the core hypothesis here. And I think the core hypothesis is something we call the linear representation hypothesis. Mm-hmm. So if we think about the car detector, the more it fires, the more we sort of think of that as meaning, the model is more and more confident that a car is present. Or, if it's some combination of neurons that represent a car, the more that combination fires, the more we think the model thinks there's a car present. This doesn't have to be the case, right? Like you could imagine something where you have this car detector neuron and you think, if it fires like, between 1 and 2, that means one thing, but it means like totally different if it's between 3 and 4. That would be a nonlinear representation. And in principle, that, models could do that. I think it's sort of inefficient for them to do. If you try to think about how you'd implement computation like that, it's kind of an annoying thing to do. But in principle, models can do that. So one way to think about the features and circuits sort of framework for thinking about things is that we're thinking about things as being linear. We're thinking about there as being that if a neuron or a combination of neurons fires more, it's sort of that means more of a particular thing being detected, and then that gives weights a very clean interpretation as these edges between these entities, these features, and that edge then has a meaning. So that's in some ways the core thing. It's like we can talk about this sort of outside the context of neurons. Are you familiar with the word-to-vec results? Mm-hmm. So you have like, king minus man plus woman equals queen. Well, the reason you can do that kind of arithmetic is because you have a linear representation.
Can you actually explain that representation a little bit? So first off, so the feature is a direction of activation.
Yeah,
you can
exactly.
think of it that way. Can you do the minus men plus women, that the word2vec stuff. Can you explain what that is?
Yeah, so
That
there's this very...
It's such a simple, clean explanation of what we're talking about.
Exactly, yeah. So there's this very famous result, word2vec by Thomas Mikolov et al., and there's been tons of follow-up work exploring this. So sometimes we create these word embeddings where we map every word to a vector. I mean, that in itself, by the way, is kind of a crazy thing if you haven't thought about it before, right?
Mm-hmm.
Like we're going in and we're turning, like if you just learned about vectors in physics class, right? And I'm like, oh, I'm going to actually turn every word in the dictionary into a vector. That's kind of a crazy idea. Okay, but you could imagine all kinds of ways in which you might map words to vectors. But it seems like when we train neural networks, they like to go and map words to vectors to such that they're sort of linear structure in a particular sense, which is that directions have meaning. So, for instance, if there will be some direction that seems to sort of correspond to gender, and male words will be far in one direction, and female words will be in another direction. And the linear representation hypothesis is, you could sort of think of it roughly as saying that that's actually kind of the fundamental thing that's going on, that everything is just different directions have meanings, and adding different direction vectors together can represent concepts. And the Mikolov paper sort of took that idea seriously, and one consequence of it is that you can do this game of playing sort of arithmetic with words. So you can do king, and you can subtract off the word man and add the word woman. Mm-hmm. And so you're sort of going and trying to switch the gender. And indeed, if you do that, the result will sort of be close to the word queen. And you can do other things, like you can do sushi minus Japan plus Italy and get pizza, or different things like this, right? So this is in some sense the core of the linear representation hypothesis. You can describe it just as a purely abstract thing about vector spaces. You can describe it as a statement about the activations of neurons. But it's really about this property of directions having meaning. And in some ways, it's even a little subtler than that. It's really, I think, mostly about this property of being able to add things together. That you can sort of independently modify, say, gender and royalty, or cuisine type or country and the concept of food by adding them.
Do you think the linear hypothesis holds? That kind of carries scales?
So far, I think everything I have seen is consistent with this hypothesis, and it doesn't have to be that way, right? Like you can write down neural networks where you write weights such that they don't have linear representations, where the right way to understand them is not in terms of linear representations. But I think every natural neural network I've seen has this property. There's been one paper recently that there's been some sort of pushing around the edges. So I think there's been some work recently studying multi-dimensional features, where rather than a single direction, it's more like a manifold of directions. This, to me, still seems like a linear representation. And then there's been some other papers suggesting that maybe in very small models, you get nonlinear representations. I think that the jury's still out on that. But I think everything that we've seen so far has been consistent with the linear representation hypothesis, and that's wild. It doesn't have to be that way, and yet I think that there's a lot of evidence that certainly, at least, this is very, very widespread, and so far the evidence is consistent with it. And I think one thing you might say, well, Christopher, that's a lot, to go and sort of to ride on. If we don't know for sure this is true, and you're sort of, you're investigating neural networks as though it is true, isn't that dangerous? Well, but I think actually there's a virtue in taking hypotheses seriously and pushing them as far as they can go. So it might be that someday we discover something that isn't consistent with the linear representation hypothesis, but science is full of hypotheses and theories that were wrong, and we learned a lot by sort of working under them as a sort of an assumption, and then going and pushing them as far as we can. I guess this is sort of the heart of what Kuhn would call normal science. I don't know. If you want, we can talk a lot about philosophy of science, and
that leads to the paradigm shift. So yeah, I love it, taking the hypothesis seriously and take it to a natural conclusion.
Yeah.
Same with the scaling hypothesis. Same.
Exactly. And
I love it.
One of my colleagues, Tom Hennigan, who is a former physicist, made this really nice analogy to me of caloric theory, where once upon a time we thought that heat was actually this thing called caloric, and like the reason hot objects would warm up cool objects is like the caloric is flowing through them. And like because we're so used to thinking about heat in terms of the modern theory, that seems kind of silly, but it's actually very hard to construct an experiment that sort of disproves the caloric hypothesis. And you can actually do a lot of really useful work believing in caloric. For example, it turns out that the original combustion engines were developed by people who believed in the caloric theory. So I think there's a virtue in taking hypotheses seriously, even when they might be wrong.
Yeah.
Yeah.
There's a deep philosophical truth to that. That's kind of like how I feel about space travel, like colonizing Mars. There's a lot of people that criticize that. I think if you just assume we have to colonize Mars in order to have a backup for human civilization, even if that's not true, that's going to produce some interesting engineering and even scientific breakthroughs, I think.
Yeah, well, and actually, this is another thing that I think is really interesting. So, there's a way in which I think it can be really useful for society to have people almost irrationally dedicated to investigating particular hypotheses, because well, it takes a lot to sort of maintain scientific morale and really push on something when most scientific hypotheses end up being wrong. A lot of science doesn't work out. And yet it's very useful to go just there's a joke about Jeff Hinton, which is that Jeff Hinton has discovered how the brain works every year for the last 50 years.
Yeah.
But I say that with with really deep respect, because in fact that's actually that led to him doing some really great work.
Yeah, he won the Nobel Prize now. Who's laughing now?
Exactly.
Yeah.
I think one wants to be able to pop up and sort of recognize the appropriate level of confidence, but I think there's also a lot of value in just being like, I'm going to essentially assume, I'm going to condition on this problem being possible or this being broadly the right approach. And I'm just going to go and assume that for a while and go and work within that. And push really hard on it. And if society has lots of people doing that for different things, that's actually really useful in terms of going and getting either really ruling things out, right? We can be like, well, that didn't work, and we know that somebody tried hard, or going and getting to something that it does teach us something about the world.